Welcome to The Explainer. Today we are going to tackle a really powerful tool in data science. It's called Principal Component Analysis, or PCA for short. It's an absolute game changer for simplifying complex data. So let's just dive right in.
So let's just kick things off with a question. What if you could take this massive, complex pile of data and just simplify it? Cut through all that noise to find the real secrets, the important patterns hiding right there inside. Well, that's exactly what PCA is designed to help you do.
Okay, so to really get why a tool like PCA is so useful, you first got to understand the problem it's built to solve. And that problem is, well, it's having way too many features or dimensions in our data.
You know, when your data set has dozens, maybe hundreds, or hey, even thousands of features, it just becomes this huge headache, right? It's super expensive for computers to process, it's pretty much impossible for us humans to visualize, and, get this, it can actually make our machine learning models perform worse.
So, what do we do about this? How do we tackle it? Well, the answer is all about finding a better, smarter way to look at our data. A more efficient angle, if you will. And that's the whole idea behind PCA.
So what is it really? At its core, PCA is what we call a dimensionality reduction technique. It sounds complicated, but all it really means is it takes all your original features and transforms them into a brand new, smaller set of features. The cool part? This new set still holds on to most of the really important info from the original data.
Okay, here's a great analogy to help wrap your head around this. Imagine your data is like a big, messy cloud of stars scattered across the sky. From where you're standing, it might just look like a random jumble, but PCA is like finding that one perfect spot to stand, that one perfect angle, where suddenly the true shape and structure of that star cloud just pops out at you. It becomes crystal clear.
All right, so we've covered the what and the why. Now for the fun part, the how. Let's break down how this thing actually works, step by step. But wait, before we jump into the steps, there are two key concepts from linear algebra we kind of need to touch on. These are the engines that make PCA run. First up, you have eigenvectors. Just think of these as defining the new directions in our data, those new angles we're going to look from. And then you have eigenvalues. These guys measure the importance of each of those new directions. They tell us just how much of our data story is told along that new line.
The whole process really boils down to four main stages. First, we standardize the data. This is super important because it puts all our features on a level playing field. So things like age and salary are treated equally. Second, we calculate something called the covariance matrix. It's just a fancy way of figuring out how all the original features move and vary together. From that matrix, we find our principal components. And finally, the last step is to transform our original data onto these new, much more insightful axes.
And if you remember one thing about that whole process, let it be this. PCA is obsessed with finding the spread, or the variance, in your data. It works on this really simple but powerful idea. The directions where your data is most spread out, well, that's where the most interesting information is hiding.
Okay, this is where the magic happens. Let's actually see the payoff. We're going to look at a before and after to see the real impact of applying PCA to a dataset.
So before PCA, if you just grabbed any two of your original features and tried to plot them, you'd probably get something that looks, well, like a mess, a confusing jumble of dots. There's just no guarantee that those original axes are going to show you anything useful, like clear groups or patterns in your data. But after PCA, oh man, the story completely changes. We project that same data onto its top two principal components, those new axes with the most variance, and bam, the underlying structure just reveals itself. The groups become clearer, the hidden patterns pop right out. It's the exact same data, we're just looking at it from a much smarter perspective.
Now, of course, like any tool, PCA is awesome. But it's not a silver bullet. It's not the perfect solution for every single problem. So it's really important to know where it shines and, where it has its weaknesses.
So on the plus side, it's absolutely fantastic for things like data compression or for handling features that are all tangled up and correlated with each other. But there is a downside. The new components it creates, they're these mathematical combinations of your original features, which can make them really hard to explain in, say, a business meeting. PCA is also super sensitive to how you scale your data, which is exactly why that standardization step at the beginning is so critical.
All right, so let's wrap this up with the key takeaways. What should you remember? PCA is a super powerful tool for simplifying your dataset. It cuts down on your features while holding on to the most important patterns. And it does this by finding the directions where your data varies the most.
The end result? Your data becomes way easier to visualize and to feed into your models.
And that really leaves us with one last thought to chew on. By taming all that complexity, PCA doesn't just tidy up your data, it opens up a whole new world of possibilities for discovery. It gives you the power to find that crucial signal hidden in all the noise. So the real question is, now that you can do that, what will you discover?